Welcome to In the Know Medical Imaging, where we make medical imaging easy to understand. Dense breast tissue can sometimes act like camouflage, hiding small abnormalities on standard 2D X-rays. How does 3D mammography see through overlapping tissue layers? Today we are exploring digital breast tomosynthesis. We will explain what patients experience during a 3D scan while breaking down arc acquisition physics, synthetic 2D image reconstruction, and microcalcification analysis for our technologist community. For patients, having a 3D mammogram feels almost identical to a traditional 2D mammogram. The positioning and compression paddle feel the same, but as you hold still for a few seconds, the X-ray arm sweeps smoothly in a short arc over your breast. It takes a series of low-dose pictures from multiple angles, allowing us to build a detailed 3D image. Think of a 2D mammogram like looking at a closed book. All the pages are stacked on top of each other. A 3D mammogram allows us to flip through that book page by page. For patients with dense breast tissue, this page-by-page view prevents overlapping tissue from hiding small tumors or creating false alarms, leading to earlier detection and far fewer unnecessary callback visits. For our mammographers and student community, digital breast tomosynthesis relies on limited-angle tomography. During acquisition, the X-ray tube pivots across an angular arc, typically between 15 and 50 degrees, firing a series of low-dose projection exposures onto a high-resolution flat panel detector. Wider sweep angles increase Z-axis depth resolution, while narrower arcs shorten scan times to minimize patient motion. Once raw projection data is captured, advanced mathematical algorithms reconstruct the volume into thin focal planes. Iterative reconstruction and filtered back projection process these low-dose projections into a stack of 1 millimeter reconstructed slices parallel to the detector. Browsing through these thin slices eliminates tissue superimposition, making subtle spicular masses and architectural distortions clear. To minimize patient radiation dose, modern DBT platforms incorporate synthetic 2D technology. Instead of acquiring a separate 2D exposure alongside the 3D sweep combo mode, reconstruction software mathematically synthesizes a 2D image directly from the 3D dataset. Utilizing synthetic 2D software maintains overall diagnostic sensitivity while reducing patient radiation dose by up to 45%. Technologists must recognize how different pathologies present across 2D and 3D modalities. Spicular masses and subtle structural distortion are best detected on 1 millimeter 3D slices because tissue overlap is removed. However, evaluating cluster shapes of tiny microcalcifications still requires high detector pixel resolution, making high magnification 2D views or synthetic maximum intensity projections essential. Uniform tissue compression remains fundamental to quality breast imaging in both 2D and 3D acquisitions. Proper compression flattens tissue thickness, reducing X-ray scatter, preventing motion blur, and lowering the required radiation technique. Under regulatory standards like MQSA, the mean glandular dose for a standard screen film or digital view must remain well below safety limits, and 3D technology easily complies with these thresholds. Digital breast tomosynthesis has transformed screening mammography worldwide. Clinical studies consistently show that 3D mammography increases the detection of small invasive breast cancers by up to 40%, while simultaneously dropping unnecessary patient recall rates by 15 to 30%, bringing peace of mind to patients. 3D mammography uses limited-angle X-ray arcs and advanced reconstruction to see through dense tissue safely and clearly. Thanks for watching! If you learned something today, make sure to like, comment, and subscribe, and check out our merch store for more cool medical imaging items.